In this video, I demonstrate the setup of RAGFlow on AWS using the live scripting approach. RAGFlow is an open source platform that combines agentic AI capabilities with an advanced RAG engine. As an example, I have uploaded car manuals into my knowledge base and created a chat for this in RAGFlow. I open it, start a new conversation, and type in my question. The wipers of my Ford Transit stopped working. I suspect a blown fuse. RAGFlow searches the knowledge base and generates an answer based on the retrieved data. It recommends to check the fuse F32, which protects the windshield wiper motor. I can see the chunks related to this assertion and directly open the corresponding document on the linked page to verify it. Jumping directly to the linked reference is a big advantage of RAGFlow. In this video, I will demonstrate how to deploy RAGFlow on AWS. We'll start in a terminal, either a system terminal or a vTerm in Emacs, and use Terraform to create an EC2 instance with GPU and a security group in the AWS cloud. Next, we'll connect via SSH and set up the software stack, which consists of the Docker engine, NVIDIA drivers, and several additional tools. Then we launched the Docker environment, which includes an Nginx reverse proxy, the RAGFlow core container, an executor container, as well as additional containers for supporting services. We will also generate self-signed certificates and configure HTTPS, as the platform will be accessible from the internet. In a short demonstration, we will register through the web UI and upload a sample document to our RAGFlow instance. Then we will create a chat dialog, query the knowledge base, and receive an AI-generated response. Finally, a cleanup section will remove all resources created during the installation. Let's start by bootstrapping the project. I open my browser and navigate to the github.com Andreas Wittmann private-rag page. This repository contains all the documentation and configuration needed to set up this installation. We are particularly interested in the file private-rag awsgpu.org, which is an Emacs org mode file containing live scripting setup instructions. Following the live scripting approach, there are also a PDF version available for offline reading and a static HTML page, both generated from the org mode file for improved readability and navigation. I scroll down to the bootstrapping section, copy the instructions into a terminal, and execute them. This creates a labs directory and clones the GitHub project locally. Next, I launch Emacs and open the org mode file. From there, I click the link to the HTML version, which opens a beautifully styled single-page document complete with a navigation bar and syntax highlighting. I'll be using the live scripting approach throughout this video, which is briefly explained in the live scripting methodology section. Essentially, this approach allows us to use the Lisp function sendLine to vTerm to execute the current line from the org mode file directly in the Emacs vTerm terminal. Back in Emacs, I navigate to the section Setting the Project Foundation. Start a vTerm session and follow the instructions simply by pressing my F4 key, which I have bound to the sendLine to vTerm function. I switch back to the project directory and verify the default VPC, test the AWS CLI by listing an S3 bucket, and check whether Terraform is installed. In summary, the private RAG project has been successfully cloned to the local machine, and both AWS and Terraform are properly configured. I continue with the infrastructure as code section and begin by generating SSH keys. I navigate back to the project directory, verify that no old SSH keys are present, and then create a fresh key pair. Next, I move on to the Terraform configuration. I switch into the Terraform directory and create a tfvars file containing all the settings required to provision the AWS infrastructure. After reviewing the file, I initialize Terraform, then format and validate the Terraform files. I then proceed to the deployment planning section. Using the variables defined earlier, I create a Terraform plant file, tfplan. I convert this plan into a human-readable format and review the resources that Terraform is about to create. In total, Terraform will create 8 AWS resources, including security group rules, an elastic IP, and a GPU-enabled EC2 instance based on an Ubuntu AMI. Next, I move to the deployment execution section. I apply the plan using Terraform apply. After a short time, all resources are successfully created, and I verify the outputs. Everything looks good. I list the EC2 instance, inspect its details, and store its public IP address in an environment variable for later use. I then continue with the SSH configuration section. Because my public SSH key was injected into the EC2 instance via Terraform, I can now perform a simple SSH login test using the private key. The key-based authentication works as expected. I add the newly created EC2 instance to the local SSH config file and verify the file using a Perl one-liner. Finally, I test SSH access again, this time using the alias defined in the SSH config. The next section, GPU instance selection and upgrading, explains different instance type options and shows how to switch between types using Terraform. In summary, I have successfully provisioned the AWS infrastructure using Terraform and launched a GPU-enabled EC2 instance. SSH access is set up and tested and working correctly. In the next section, GPU verification, I install NVI-top, a monitoring tool for the GPU, and check the status of the NVIDIA drivers as well as the CUDA version. I run a quick test to confirm GPU support in Docker. I jump to the next section, which covers the installation of some tools, but I only look at the Docker part and skip the Python development section, since I don't plan to develop in this environment. In the Docker engine installation section, I run another quick Docker test. Check the Docker Compose version and verify that Docker is installed as a system service for automatic startup on machine boot. I install lazy Docker to monitor the machine via an SSH terminal connection. I skip the next two optional sections, which cover configurations for the development environment. The system is now ready for RAGFlow deployment. Now I move to the RAGFlow deployment section. In basic RAGFlow setup, I log in to the EC2 instance, clone RAGFlow from the official GitHub repository, and change into the RAGFlow directory. Next, I configure the containers for GPU usage by enabling the executor service, uncommenting it in the Docker Compose file, and fix a bug that was calling the wrong entry point script. Now I can start RAGFlow with Docker Compose. While this takes a while to download the images and start the containers, I open a terminal to monitor the Docker and machine resources. I use iTerm2, open 3 terminal tabs in split view, and log into the EC2 instance in all 3 terminal windows. In the first terminal, I start htop to monitor the CPU and RAM resources. In the second, I start NVI-top to monitor GPU usage. In the third terminal, I start lazy Docker to monitor the containers. I speed up the video until RAGFlow has started completely. Back in Emacs, I check the Docker processes, get the public IP address, and point my browser to RAGFlow's web page to verify that it is running. Okay, it's running. Before I continue working with RAGFlow, I want to configure HTTPS, so I shut down Docker Compose and move to the next section, HTTP setup. This HTTP setup section consists of 5 steps. In the first step, I create an SSL directory and use OpenSSL to generate self-signed certificates with the command name localhost. I set the correct permission on the key files and list them to verify they were created properly. In the second step, I back up the existing HTTPS configuration and then use SED to update the domain and proxy paths. In the third step, I need to update the Docker Compose YAML to include the key files and HTTPS configuration in the volumes section. This is best done with Visual Studio Code using the remote development extension. I simply connect VS Code using the SSH alias of the EC2 machine. Here I open the RAGFlow directory and navigate to the Docker Compose YAML file. I need to copy the configuration twice, once for the RAGFlow CPU service and once for the RAGFlow GPU service, although in this video I only used the GPU service. In step 4, I start Docker Compose and verify that the containers are running. In step 5, I verify HTTP access using curl. The HTTP address is now redirected to the HTTPS address, and the HTTPS address also responds correctly. I also check the certificates and the health of the RAGFlow API. I also verify GPU functionality in the running RAGFlow GPU container. I update the HTTP links and am ready to use RAGFlow in the UI. In summary, the RAGFlow environment is installed and configured with GPU support and HTTPS, and it is accessible in a web browser over the internet. In this short example, I'll demonstrate how to ingest a PDF document into RAGFlow. I'm using a PDF stored in the project's example docs directory. It's a publicly available scientific paper on prompting techniques. The document has a complex layout with many diagrams and spans 76 pages, making it an excellent candidate to showcase the quality of RAGFlow's DeepDoc parsing engine. I begin by opening RAGFlow in my browser and registering with the default credentials email, admin@ragflow.io, password admin. After registering, I log in with these credentials. The first step is to configure access to external LLMs in the configuration section. I add my API keys for Anthropic and OpenAI, then select the desired models in the default settings menu. Next, I create a new data source, which in RAGFlow terminology represents a knowledge base. Here I set the embedding model, choose DeepDoc as the parsing method, and keep the remaining default settings. I then upload the PDF directly into the knowledge base and start the parsing process. DeepDoc parsing is compute intensive and takes some time to complete. To monitor system activity during parsing, I use LazyDocker and NVITop. You can see how RAGFlow and the executor container process the document in parallel, while NVITop displays GPU usage and specific process utilization. I'll fast forward the video until parsing is complete. Back in the RAGFlow UI, I can now inspect the generated chunks and run a test query to verify that the knowledge base is functioning correctly. For example, I search for the term RAG and confirm that it appears in one of the chunks. Next, I create a chat based on this knowledge base. I select the dataset I just created and choose Claude Sonnet 4 RAG.5 as the LLM. I start a conversation and ask, what is RAG? RAGFlow searches the knowledge base and generates an answer based on the document content. Here's the answer. RAG, or Retrieval Augmented Generation, is a paradigm in which information is retrieved from an external source and inserted into the prompt. Hovering over the reference icon, I can see the corresponding chunk. I open it and can verify that this information comes from the paper. This concludes the brief RAGFlow demonstration. In the chapter Infrastructure Cleanup, I tear down the entire environment and remove all resources and files that were created throughout the process. I start by jumping to the Lifecycle Operations section in the appendix and stopping the EC2 instance. To do that, I initialize my shell environment, retrieve the instance ID of the EC2 instance, check its current status, and then stop it. A small loop notifies me once the instance has fully stopped. Next, I move to the section Decommissioning with Terraform and destroy all resources that were created by Terraform. Afterwards, I verify the results by listing my EC2 instances again. The instance should now show the status terminated. Then I switch to the section Cleanup SSH, where I use a Perl one-liner to remove the EC2 instance entry from my SSH config file. I also delete the SSH keys that were generated earlier. I then skip the Cleanup Terraform States section and jump straight to Verify Complete Cleanup. Here I double-check that all AWS resources have been removed. I review the EC2 instances, the security groups, and the key pairs. Finally, I delete the private RAG project directory. In summary, both the AWS environment and all local configurations and files have been completely cleaned up. At its core, the live scripting approach I used here is idle for creating, documenting, and consuming complex IT solutions. In this demo, I focused on consuming the solution. A fully functioning RAGFlow environment serves as an excellent foundation for modifying the live scripting file and extending the solution or deploying it to other platforms. I have been using live scripting in professional environments for many years, and I have recently extended this technique with AI tools such as GitHub Copilot integration for Emacs and a live scripting mode for the AI coding tool KiloCode. This concludes the presentation on running RAGFlow in the AWS cloud.